So, this is the first time I've ever done this, so hopefully it will work. I'm actually recording my screen and talking to it at the same time. It's a brave new world. Just going to show you y equals sine x. Plot it on here. I know you know what it looks like. There we go. Don't forget everything's in radians. Let's zoom in a little bit. Okay, and so it does a complete cycle over a distance of 2 pi, because 2 pi radians is a full circular turn. So there we are. That's what sine x looks like. Now, it'd be quite interesting to see if we can find a function that looks a bit like sine x, that you don't need to know the values of sine x for the function sine x itself. I mean, nobody knows, for example, what sine of 2 is off the top of their head, and you rely on your calculator, you type it in, and out comes the answer. So wouldn't it be great, at least sort of hypothetically, or you know, as a sort of point of interest, to see if there's a function that's the same as sine x, that is just a polynomial, say. So I thought, well, let's start with y equals x, simplest polynomial function of all. I suppose y equals 1 is a bit simpler, y equals 0. There we are. They don't look the same, do they? It's not doing the job. But it kind of is if you zoom in on this part of the graph here. It does a very good job around 0, but it rapidly loses its effectiveness once you get past round about 0.5. So can we improve it? Well, it turns out we can, because if I add an extra term on the end of it, let's try adding an x squared. So let's try taking an x squared off to try and make it come back down again. That's not working very well. Let's try x cubed. That's interesting. It's kind of a similar sort of shape, putting that x cubed on there, but it's not. It's going down too fast and up too fast here. So let's temper him a little bit. Let's slow him down a little bit by scaling it a little bit, putting in a value here. So let's try 2. Okay, 3, 4, 5, 6. I'm going to go with 6. There we go. Oh, look at that. That's hugging nicely now. Don't forget, we only actually need it to hug nicely up to here, really. Sorry, I got that wrong, didn't I? Up to here, because if it hugs nicely up to here, that's a full cycle. Okay, that would be a full cycle and all would be well. So let's add another term. Now, we missed out square, so I'm going to miss out to the power 4 and go straight to the power 5. Oh, that's gone shooting off again. So let's temper him again. Whoops. By dividing him by something. So this time I'm going to divide him by 120. Don't ask me why at the moment. All that will be revealed later. And look, that's looking really good now. Now there's a bit of a pattern developing here. The next one's going to be x to the power 7. And I'm going to divide this one by 5040. These numbers are not arbitrary, by the way. You might have already worked out what they are. Probably not, but you might have done. But we'll come to that later. X to the 9 next, divided by, and this one would be divided by 362880. I'm not making these up. These are the correct values. Well, we're getting there. We're not quite getting the perfect shape up to 6. I suppose you have got a full cycle if you start there and finish there. So that would actually do a really, really good job to allow you to find the value, sine of any value you like. You just plug in the value you want. So sine of 2, say you wanted sine of 2, rather than just relying on your calculator, you could do it by hand now. You could put 2 in there, and there, work out the answer. It will only take a couple of seconds, and you'll know what sine of 2 is. Well, this is called a power series. I love the name. That's how I would introduce them at university. They're called power series. Also sometimes called a Taylor series, or specifically in this case, Maclaurin series. Okay, but let's not worry about the names. these series, it turns out that most functions, such as sine x, cos x, e to the x, ln x, and many other things, can be approximated using one of these series here. I say approximated, we can actually do better than that. If I added sufficient number of terms here, I can actually get this to be sine x, exactly the same as sine x. The only snag is it's an infinite number of terms. Now obviously I can't type in an infinite number of terms, and it will take me a long time to type them in individually. However, what I can do is use the sum function here to replicate a large number of them. I'm gonna put so I can add a slider and actually show you what. Oh crikey! What on earth am I doing? If I put an a there like that, I can alter the value of a and have more and more terms. So all I need to do now is to find a way of representing the pattern that's going on here. And well, let's start with the x. That's the easy one. It's x to the power of, now if you look at this, it's 1, 3, 5, 7, 9. Well, that's an nth term rule thing, isn't it? And it would be shut up iPad, that would be 2n minus 1. So if I go like, I have to put it in a bracket, 2n minus 1 like that, then let's add the slider now. There you go. So that is with a equal to 1, so that is x to the power of 1. So it's y equals 1. So it's that purple, y equals x, that purple line there. Now, if you look, the next thing I need to replicate is the sign, because that keeps altering. It goes plus, minus, plus, minus. So to do that, what I need to do is I need to do minus 1 to the power of n plus 1. Okay, and that will mean that each term, as it goes along, the sign will keep changing from well, the first one, when you put a 1 in there, you'll get 1, so it'll be positive. If you put a 2 in there, it'll be the second term, you'll get minus 1 cubed, which will be minus 1, so you get that minus sign. And it'll keep altering the signs as we go along. Okay, and the final thing I need to replicate is this thing on the bottom here. Now this thing on the bottom here, I'll tell you now, is that's 3 factorial, that's 5 factorial, that's 7 factorial. So it's the same as the power of the x with a factorial on the end. So I need to divide by 2n minus 1, which will give me the correct value for the factorial like that. And that's it. So that there is, well, it's not infinite, so however big I want it to be, an expansion of, I wonder if I can, how do I do this? I want to change the step size. Here we are. So we'll start at 1 and we'll go up to, oh, let's go mad, let's go up to 50 in steps of 1 like that. I think that's right. Oh god, I don't know what I'm doing. Right, you ready? Here we go. So 1, 2, 3, 5. Oh, I've lost count already. Look what's happening as I go along. It's hugging. It's hugging. I'm off the end of the screen now. I'm only up to 20. I go up to 50. There we are. And I'll start scrolling along and look at that. Oh, it loses it. Oh, crikey, it's gone mad down there. But I think that's pretty good. And that's 50. Struggling to keep up now, look. That's up to 50. So anyway, that was a short video to show you that it's possible to replicate y equals sine x with an infinite series of polynomial type terms. An infinite polynomial. I'm going to show you why. I'm going to try anyway.